Hi everyone, welcome back to another Calculus 12 video. So today we're looking at trigonometric substitution, and we're just going to run through a couple of examples because I think you'll find it's quite similar to what we looked at last day. I know I say that every day, but substitution is the same thing as what we've been doing in algebra, and then we also did it last day, but it wasn't with trigonometry. But still the same approach or same principle that we're going to use. And so we're just basically going to look at this cos theta, and what we're going to do is we're going to substitute and let u equals cos theta. So that's the first step, is pick out the part of the equation that you are going to substitute. And once you let's make it sine theta, the sine theta that's up top. So let u equal sine theta, and then we'll also take the derivative of it. So we would have du d theta, because the derivative of u with respect to theta, because theta is embedded within the equation here. And we know that the derivative would be just cos theta when we work on that. Okay, and then we were working with substitution. This is sort of going back to stuff that we did last day, but we want to get the du by itself. So I actually am going to bring this over, and we're going to say du equals cos theta d theta. So it's still the same thing. I've just rearranged it, and you'll see the reason why we're rearranging it that way in just a moment. So taking a look at this, after working our way through that, I'm going to say this. Therefore, what we had originally here would be, well, if you take a look at it, actually, can I do this? I can do this. I'm going to use my different colors to help make this clear to you. Notice that we have cos theta, d theta, so it's like we've sort of separated it if you look at it, the two separate sides there. And then I also have that here. So I can sort of rewrite this to say this part here, take what I had there, so take e to the power of sine theta, and then if I just take those two and put them together, I know that's the same thing as du. So I can say e to the u du, which was this du here, because that's all equal to cos theta d theta, like we had in the original equation up top there. So pause if you need to, take a look at that, and make sure you understand where that's coming from. And, well, actually, e to the sine theta, well, we had said that sine theta is equal to u, so I could say eu du. And then to put it all together for my final answer, I can substitute back in. That's always the last step of what we do with this. So we can say e to the power of sine theta plus c, because remember we always have to account for the constant that might have been there when we took the derivative originally. So I'll zoom out so you can see all of it. I hope that you're able to sort of see the big picture and put that all together. Okay, so that gives you a general sense of what we're working with, and then we'll look at, you know how this works. It's the same old thing, but there's a little bit more going on in here. So, oh boy, I don't know what happened here. Let me see if I can fix this. It does this when I hit record for some reason. I might have to rewrite this. That's okay. I'm going to move this to a place where we can see it. Look at that. Oh, that didn't help. Okay, we can just work our way around it. Maybe I'll have to stop being lazy and just rewrite it. So, let me rewrite this down below where we can see. So we're integrating this from 0 all the way up to pi over 2, and we have cos cubed x, and we have sine to the power of 4 of x dx. So we can just get rid of all this and work with this. We're evaluating this complex looking thing that's not going to be such a big deal once we break this down. It looks pretty intense right now, but this is what we always do, right? We simplify and break things down as much as possible, and that will make things a little bit easier for us to work with this. So, this is a lot of stuff all at once. I'll build in some review because it's been a little while, but when we're always looking for strategies and methods to work with this and to simplify and to break things down. So, one of the things that you would look for are your trig identities, remember all the trig identities in Pre-Calc 12, or I know some of you haven't taken that before, so I gave you that sheet with the formulas on them, and of course you can use those again if you want. But we would look for some sort of creative way of breaking this down. And so I hope that you're able to recognize this, but there is a Pythagorean identity within there, but I need to separate this a little bit in order to be able to work with it. So the Pythagorean identity deals with cos squared x. I'm just going to rewrite this. I'm going to say cos squared x, and I'm going to just separate and put cos x beside it. So I've just, same thing, this and this are the same thing. I've just separated them and rewrote them. And you'll see this and recognize this, hopefully, as a strategy as you're working your way through it. I've purposely chosen one of these because I felt this would be a lot for you to try to pick out or recognize just on your own initially. Okay, and then as you're working your way through this, if we sort of zoom in and look at this part here, from our trig identities, we know that that's the same thing as 1 minus sine squared x. So again, you could use your little sheet to refer back to your trig identities if you need to, or hopefully after we practice this a bit, it's going to come back to you. And then the rest of it is still there. I'm getting lazy and don't want to rewrite this, but I will. And then we have the cos x there, and then we have our sine to the power of 4x dx. And so as we're working our way through this, I have options of how I could go through this, but I'm purposely going to choose to put the signs all together, because I know the title for today and what we've been practicing and working on is substitution. So if I can work with or get the signs together, it'll make it easier for when I'm working with my substitution. So we'll go here from 0 to pi over 2. And when we do that and multiply this all out, we would have sine to the 4x minus sine to the power of 6x. And then the whole thing would still be times cos x dx. So I'm going to show you all of that so you can still sort of see the thought process, where it came from. Again, the nice thing about this is you can hit pause at any point if you need to sort of soak it in or make sure you've understood where we got this from. And then, since we can see there's a lot of stuff going on here, we can start to do our substitution part. So let u equals sine x, because clearly that's going to make this much simpler or easier to work with. Okay, so, and then if we do that, we know that du, I would say du dx, but I'm just going to do it all in one shot. That would be equal to cos x. Actually, you can see that. Du dx would be equal to cos x, right? Same old thing we've been doing. Or I can just right off the bat move that dx up top because I know where this is headed. I know that that's what I'm going to be using or working with. So that makes things a little bit easier for me. So I hope that this is okay, but I'm going to scroll up so we can just focus on this part that we're dealing with right now. Okay, so then if we take a look at these little portions here, the 0 and the pi over 2, well, we want to find this when x equals 0, then u would be sine of 0, which if you can either think back to your graph of what sine x looks like, remember that, or if you want to use your unit circle, whatever helps you, but we know that that is equal to 0, right? So again, drawing on some of that past knowledge, but I know we're all coming at this with different areas of expertise and background. So hopefully this little bit of review will help. Then we also want to do this for the other portion of it. So when x equals pi over 2, then my u would be sine of pi over 2. And again, you can look at this. Remember, like partway through would be pi because the whole thing's 2 pi. So then this middle part here would be pi over 2. So we can see that at pi over 2, that would be our y value of 1. So this is making it a little bit easier for us to sort of like break it down and work our way through it. Because again, if we go back to the original, that's pretty intense looking. But hopefully with the substitution, you're finding it's not too bad. Okay, so therefore, let's go back to what we were working with. When we integrate from 0 to pi over 2 of cos cubed x sine to the 4 dx, that would be the same thing as saying 0 to pi over 2 of what we just came up with, sine to the 4x minus sine to the 6x times cos x dx. Oh, I gotta shrink this so you can see it. So basically all I'm saying is our original that we started with, we broke that down and found it was the same thing as this stuff on the right. So we can now take that and apply it to make it a bit easier by now taking it one step further and plugging in our u stuff here. So again, if we have, I can change this, and since I found that it's 0 to 1, when I figure out what the u value is, I can redo this and simplify it to say if I'm integrating from 0 to 1 of u to the, so this part, I feel like I should do that in purple. Notice what we have here, u equals sine x, so I could say this is u to the 4, right? So taking care of that part there. And then minus sine to the 6x, so I could say minus u to the 6. And then cos x dx, remember this part here? Thank God for my colors, because how would you ever even see this or recognize this? But looking right here, remember cos x dx is equal to du, so I can actually write du in here. So you see how all the pieces are coming together and the thought process behind this. So the first step, just like last day, is we substitute and let u equal something. And you could pick another variable, but use a common one that we usually use. And then you take the derivative of it. And then you rearrange that derivative to make it work in your equation. So usually you want the du by itself. So how it was du dx, we move the dx up top. So hopefully this is sort of coming together and you're seeing where this came from. And now we can integrate this. If we were to work or think backwards with this, we would get u to the 5 over 5 minus u to the 7 over 7. Because remember, working our way backwards, if we were taking the derivative, this would come forward and be 7 over 7 to the power of 7 minus 1, which is 6, which would give us this. I feel like that wasn't the clearest explanation, but hopefully you sort of remember that, or you can brush up on your skills on that if you need to. And then for this, we're going from 0 to 1, so we'll keep that in mind there as well. And so that just means for each of these values, we're going to plug these in. So obviously when we plug in 0, we can see everything's going to wipe out. So 1's the only thing that we're really interested in. So we would get 1 over 5 minus 1 over 7. And we can see we want a common denominator of 35. Well, it would also be minus 0, but like we don't really need to worry about that. You know if you plug in 0, it's going to be gone. So we end up with 2 over 35 when we work our way through and get our common denominator here and simplify things a little bit. So I hope that you found that helpful. 1 A, B, D, E, 2 all and 5 all is your work for the day. I hope that helps.